Welcome class in this new video where we discuss with you on more facts about eigenspace. So now eigenspace are the span of eigenvectors of a matrix related to specific eigenvalues. Now let's consider A. If we consider a matrix A, n times n matrix, and consider the set E, which is equal to the set of vector belonging to Rn, where Ax equals to lambda x. Now, what do you realize? You realize that if x is part of E, then Tx for any scalar T is also part, as we have ATx, which equals to Tex, which is equals to, we know that Ax equals to lambda x, which is equal to T times lambda x, which is equals to lambda times Tx, which proves the fact that Tx is also part of E. Furthermore, if we have that x1 and x2, two vectors of E, then Ax1 plus x2 equals to Ax1 plus Ax2 equals to, you know that Ax1 is lambda x1 and Ax2 lambda x2. We sum it, we have this equals to lambda x1 plus x2, which concludes that x1 plus x2 also belongs to E. Now, why are we explaining this? For you to know that the set of vector E is therefore a subspace because it is closed under addition and also closed under scalar multiplication, right? Now, it is obvious for you to also realize that the zero vector also belongs to this set. How then can we define in a generalized way an eigenspace? An eigenspace, therefore, an eigenspace, therefore, will be a space of eigenvector corresponding to eigenvalues, including the zero vector. So this can be written as eigenvectors of A corresponding to its eigenvalues, right? 0. Okay, so we want to make this this differentiation so that you should be aware of the fact that the eigenvector should be non-zero. So this then will be an eigenspace, right, of matrix A with respect to the eigenvalue lambda. So this can also be written as eigenvalue of A with respect to the corresponding value of lambda equals to the null space of A minus lambda I equals to 0. So the eigenspace will be the vector space of all eigenvectors corresponding to their eigenvalues. Okay, so for example, find the eigenspace of matrix A, which is equals to 1, 0, 2, 0, 3, 0, 2, 0, 1. Now we know that the first step is to solve for determinant of A minus lambda I, which is equals to 1 minus lambda 0, 2, 0, 3 minus lambda 0, 2, 0, 1 minus lambda. Taking the second row, this will be 0, 0, so I'll just remain with this. So it will give me equals to 3 minus lambda 1 minus lambda 2, 2, 1 minus lambda, which is equal to 3 minus lambda times 1 minus lambda squared minus 2 squared. Now, and if you do the factorization of this, you realize that this will give you 3 minus lambda times lambda plus 1 times 3 minus lambda with a minus here. So we realize that I have solving this equals to 0. I have that lambda equals to 3 and lambda equals to minus 1 with multiplicity equals to 2. right? Lambda equals to minus 1, yes, and lambda equals to 3 with multiplicity 2, because I have 3 here and I have 3 here. Yeah, okay, cool. Now, let's now find the eigenvector for lambda equals to minus 1. So I have to solve the equation A minus lambda I V equals to 0, which is 1, right, plus 1, right, and I have that 0, 2, and I have 0, 3, I have 0, and I have 2, I have 0, I have 1, 1 minus, which is 2, 1 plus 1, right? Here I have 3 minus 1, which is 2. Okay, now having this times x1, x2, x3 equals to 0, 0, 0. Now, this will give me that I will have that 2, 0, 2, 0, 2, 0, 2, 0, 2. Now, writing is under the as goes reduct echelon. So what we have is that if I divide the second row by 2, so I have 1 here, and if I do that, row 3 equals to row 3 minus row 1, and I divide also row 1 by 1, so I will have that 1, 0, 1, 0, 1, 0, 0, 0, 0. Right, and then from here we can easily see that x2 equals to 0, and we can see that x1 equals to minus x3. So my vector will be, which is x1, x2, x3, my vector will be, right, minus x3, right, 0, x3. So which is minus x3 or x3 minus 1, 0, 1, right? So, and if I put x3 a scalar, so this will give me that the vector is t minus 1, 0, 1 with t different from 0. Now, if let's have a look on the second eigenvalue for lambda equals to 3. So for lambda equals to 3, what do we have? We have that we have to solve this equation as well, and then this will give us that minus 2, 0, 2, 0, 0, 0, 2, 0, minus 2. So if you replace lambda by 3, you have just this. Now solving this, what do you have? You realize that if you set that row 3 equals to row 3 plus row 1, all this line will be 0. All this line, the first line will be 0, and if you divide the first line by minus 2, you have 1, 0, minus 1, 0, 0, 0, and you have 0, 0, 0. Now you can see that we can both fix x2, and we can have x1 as a fixed variable and x1, x3 as free variable. So what you have here, you have here is that if you say that x2 equals to t and x3 equals to s, so you will have that x1 equals to s, right? So this vector will be equals to x1, x2, x3. This vector will be equals to, you have 1, 0, 1, right, for s, right, plus you have t, 0, 1, 0, and then you have s and t belong to R. Yes. Now the eigenspace, you realize that now that the eigenspace of matrix A will be equals to, the eigenspace of this matrix will be equals to, I hope you can see, okay, let's write it here, will be equal to E for lambda equals to minus 1 of A equals to, okay, equals to V and a half T minus 1, 0, 1 with T scalar of R, and I have the eigenspace of 3 of matrix A equals to, let's say V1, yeah, let's say V, yeah, equals to V as well of S101 plus T010 with T and S scalar of A. Now, you may be asked to find the dimension of the eigenspace of A and eigenspace of A minus 1 and of E minus 1A and A E3A. So you can see that we have one vector here, so the dimension will be 1, and the dimension of this vector will be 2. Thank you very much. In the next video, we will expose you to the concept of diagonalization. Thank you very much. Bye.